welcome to our talk. So we manage the technology. That's what we're doing at Aurea Imaging. We are here to share our story about building the tree scout. You see they're sitting on top of a tractor. It's a device we're building for precision orchards. We started it roughly 3 years ago, and we're running lots of machine learning. So I thought it's nice to share everyone how we made it happen. Has anybody seen our talk also at the Pygrunn? Yeah, one. Yeah. We have quite an advanced technology stack, but last time when we were telling about how Python helps us with some problems, we also thought it's much more interesting to also share the machine learning part. So first, a short introduction.
I'm Navaneeth. I'm the machine learning engineer responsible for the pipeline health, model health, and make sure no apple goes undetected in an orchard.
I'm Wieneke Keller, the CTO of Aurea Imaging, so building everything around the technology. But it's not only the two of us, so I brought also a picture of the team which we built it with. And this picture also shows a little bit what kind of company we are. You see that we have black feet. It is literally covered with mud. It was during a mud milking event. But we are a technology company, but also an agriculture company. So quite often we are in the fields looking through trees, meeting our customers who are growers. So that's nice. To make sure that you actually understand a little bit our use case, because I think you are not that familiar with apple growing, I will start quickly with a short introduction in how to become an apple grower in just 5 minutes, so it won't take too long. The first question for an apple grower is, which apple is the best? What do you think? Do you see difference? Well, it's actually the middle one. If you go to the supermarket, I don't know if you've noticed it, but all the apples are roughly the same size. Well, that's not how apples are growing on a tree. They're not the same size. So what growers try to achieve is make trees grow the perfect size of apples. It gives them about 20% or 20 cents more profit per kilogram of apples. So it's quite useful to do something with your trees to get that size of apples. Then the next question is, which tree is the best? Is there blossoms in the trees? It's actually somewhere in the middle. An apple tree gets its energy, water, and it spreads all that energy over what it's growing. And if there's too much blossom on the tree, it grows small apples. And you want to have that mid-sized apple. So it's really important that trees have the optimal number of blossom clusters, because that will give that right size of apples. But if in an orchard there are like 2,000 trees per hectare, and each tree has a different amount of growth, of blossom, of what it's doing, and with precision agriculture, you can actually manage each tree individually instead of that you're doing it for all the trees together. So that's where our company is coming in. So we do precision agriculture, make sure that every tree gets the right treatment, and it's not only about making profit for the grower, it's also about sustainability with less chemicals, it's less fertilizers, because you can really give every tree what he wants. So this was kind of what our founders discovered. Well, that's really cool. There's a market in this precision farming in apple and pear growers. How are we going to help the growers with it? Let's build a tree scout. So this was the rough idea about the tree scout. You see it over here. It's a device. I have 3 slides more. I have what's in the box, but it's connecting with a precision GPS system, so we can actually do very precise location of the trees and apples and blossoms, some cloud connectivity, and it sits on top of the tractor, so you see the whole tree, so you can see whatever you want. And then the idea was that it would look like a little bit like that, so you're just driving and you're detecting trees and blossoms and everything. And then the question is, okay, if you have all of that, what can the grower actually do with it? Because we're not a data company, we're actually helping the growers, and growers are not there when they have just data. So how the process looked, or should look, that was in 2023 the idea. First you collect the data that you're doing with the tree scout, and you saw a nice picture. Then we give insights to the grower about trees with, for example, lots of blossom or not that much blossom. Based on that map, he can decide which is the optimal blossom score for me, which trees do I want to spray with a kind of chemical where part of the blossom will die. It's quite effective. So he decides by himself, okay, which tree do I want to spray and which one not. He can load the data into a sprayer, then he drives again through his orchard, and the sprayer goes on and off based on the maps we have. We have not only like the blossom spraying, there are a couple of products. I thought it's good to give you roughly an idea about how the grower works through the seasons. So in the winter, he can drive to see where the trees are. He can do it all year round, but that's where he's relatively quiet, so he has time for that kind of basic activities. In the spring, you do blossom mapping. Then when the trees start growing, you can see how fast the tree is growing, so that's figure mapping. And of course, fruit detection later on with the harvest. I can tell you much more about what he's doing with all this insight, but it gives you a little bit an idea that the Tree Scout, it can be used through the whole year. Well, until so far, it looks quite amazing. So let's build it. So you have, we started that in 23. This is a little bit how it looked like with a map and much blossom. And this is just a short slide to tell a little bit about how we're scaling. So in 23, we started with 8 customers. It was not the best season. It was also a beta season, so it was okay to fail, but we failed pretty hard. So we kind of did it over in 2024 with a different architecture where I can tell you a lot of, but that's not the topic of this talk. Then we kind of nailed the technical problems, and this year we are running quite successful now with 40 devices, even scaling to 80 next year. And you see also that it's really used quite often by our growers. And how does it look like when he's using it actually in the field? So here you see a 3-row sprayer, and you see that there's lighting on the spraying, and you see that it goes on and off based on our map, which he's imported in the sprayer. It's quite cool. A grower actually made this movie himself, so it was not our marketing department. This grower has a son who likes flying with drones. And they sent it to us and say, hey, look how cool it is. It actually works. So it's also for growers, it's quite new technology. But they're adapting it because they see the value in it. So far, about the use case, what we're doing, how we're trying to help growers. So we're now going to dive in the technology. So here you see the Tree Scout with the head off. So you look from top down. You see a big onboard computer. It's an NVIDIA computer where we're running all our software, all our machine learning models. And it's that big computer because we also want to be able to operate without internet connection. So there needs to be done a lot, or with not that much internet connection. So that's why it's a big computer. Then you see 2 ports. On tractors, we integrate with the tractor ecosystem. They integrating all the equipment via Isobus. It's kind of an old-fashioned communication protocol, but it works quite good. So we have 2 ports. One is to connect with the external GPS system, which growers quite often already have for other applications. And one is for the operating UI. It's just a small UI in the tractor where you can say start, stop. Am I connected, like the basic operating things. We have 2 cameras, of course. And the black box in the middle is to translate a little bit our software with Isobus communication. So that's on the hardware side. And then if you...
Excuse me. Is it possible for you to talk in English?
Yeah, I think...
we won't have any recording on the video.
Okay.
Sorry to interrupt you,
No, it's fine. So the machine learning part will follow, and that's where the most of you is for. So this about the hardware, what's running on board of the Tree Scout, a little bit about the technology stack we use. So we try to use as much as possible the same technology stack on the device as in the cloud. So we're running Kubernetes on both sides. You see K3S, which is a Kubernetes specially designed for the edge. We're running Python microservices on both sides. TensorRT, of course, on the edge side. So if you have questions about this, ask me. Feel free to ask when you want. And then on the edge, we're running all our models, and that's what Navaneeth is going to tell more about.
Maybe we'll just stand here.
Yeah.
Is this good? You can hear, I guess. Oh, so it's just this? Okay. Okay, let's get to the meat. So when a Tree Scout is in operation in the field, it continuously captures image from both the left and the right cameras. And to be able to get tree level insights, we need to be able to first detect the tree and locate where it is in the image. So we we need this kind of information, and we also need to detect what the objects are on the tree, like blossoms and apples. We use a computer vision model called YOLO, which is a lightweight deep neural network to be able to do this detection task. We get a bounding box and a class confidence score, which we use for further processing. We use it first also for trunk detection, blossom detection, and fruit detection. So we train it on 100 images of each class, and we test it on our test data set, and we get this. We get a accuracy of around 90%, and we'll think, yeah, we're happy with this. Let's put it on a tractor. But that's not that easy. We realize that is it done? Yeah, we realized that as problems started rolling in during production, which is the best way to learn, put your half-baked model into production. And let's go over it one by one. So the first one is real-time edge compute. We needed that because the tractor is deployed in rural environments where connectivity can be spotty at best. So what we do, we don't want images to clog up our bandwidth. So we want to do most of our processing on board and send only the processed high-level processed data to the cloud for visualization and other things. So, but luckily, YOLO is small enough. It's around 11 million parameters, which is like a fraction of one of these largest LLMs that are here. So we can run it on board of the device, but the problem is it's not fast enough. So what we do, we want to be able to capture multiple images of the tree so that we can position well and also eliminate false positives that come about. That's a simple trick to do that. I mean, it's not simple, but it is a trick that generally people use to deploy models on the edge. It's called quantization. It's basically mapping 32-bit float weights of neurons to lower precision, either float 16 or int 8. And this not only makes the compute faster, it makes the model a bit smaller. So we use TensorRT on the edge to optimize this model. We take the PyTorch model, convert it into ONNX, take a bit of the data set to calibrate the model, and this conversion happens on board of the target hardware. And by the end of it, you not only get a quantized model, but also a hardware-optimized serial model. So because of this, we got about 75% speed up from 20 milliseconds inference time down to 6 milliseconds. So now it's ready to be deployed on the edge. But then comes the next hurdle. I said we train it with 100 images, but 100 images, the variety is not representative enough for what you see in the field. So how do we do this? Because over 3 years, we went from 8 devices in Netherlands to 50 devices in 6 different countries, where each field is different. They have different apple varieties, different tree configurations, different agronomy philosophies, and even on the same field, it looks different at different times of the year. And it's seasonal, and even a single tree will look different at different times of the day because of the different lighting conditions. So there is a lot of variety that this model needs to learn. So what we decided was we need to be able to collect these varieties, and we decided to upload 1 in every 100 images to the cloud so that we can not only use it for QC, but we can add those images to the data set. But there's one slight problem with that. You'll see that here. On the day 0, we collect 100 images for annotation and training. On the right is basically the projection of the embeddings of the image for visualization. On day 2, when you deploy the model, it looks pretty similar, but it's a little more green. Day 5, you start seeing the variety that starts coming in. You have different lighting conditions, different ages of trees, and you see the spread starts getting bigger. By day 10, it becomes unmanageable. It doesn't make sense to annotate every single image that comes. So we decided to have a representation of each different cluster in the data set. So we have equal contribution from each different cluster, and starts enriching the data set. So our data set doesn't explode as we as a company scale. So that's done. Now we have a good model that's being trained as the tree scout operates more. But what we realized is maintaining a model is an iterative process, and we do the same process over and over again, and repeating process are prime candidates for automation. So we decided to automate everything, or most of it, what we can. So this is how our MLOps architecture looks like. We do have manual parts in annotation and QC, but the rest of it is automated, where we collect images, we enrich the images using 51, annotate it, then add it to the master data set, train it, deploy it, and yeah, it deploys as a init container for Kubernetes. And we test it on a Canary customer that's usually in the Netherlands, and we monitor the results, and then we decide if it's a go or no go, if we need another round of training. So this kind of speeds up the process. So that can be seen in this timeline here, our release timeline for the tree detection model, where the V1 is more than a year after the V0. But in 2025 alone, we have 5 different releases. And the last one is the problem we are still struggling with, is the lack of quantifiable metrics for these type of problems. An example of which we can see here. We trained our model to look something like on the left. The map should have looked like this, but it ended up looking like that. And it's not easy to catch these because there's no obvious error that pops up. And we were like, the only way we come to know is when the farmer calls up and says, yo, my map looks wrong. And then we look at it and we're like, okay, what's wrong? And then we dig into it. The problem here was the calibration model was a bit calibrating with a lower resolution, so it's, yeah, it did. But this would have been easy to catch if we had used the software engineering principles of testing, unit testing, integration testing, and if you have multiple apps, it's better to do cross-functional testing and definitely end-to-end testing. But how do we test these problems if your red and blue channels are switched, or if there's winter sun in your lens that blocks most of the vision, or there is blur on your lenses? And the last one is tractor paths, blocking parts of the image. So this is something that's pretty hard. And one of my favorite edge cases came as a meme in our Teams channel that, yeah, we trained for, we assume that most of our farmers drive in the daylight, but some eager customers want to try the new shiny Apple model, and they drive through the night, and we get bad map, and we're like, what's wrong? Then we look at the images, and we're like, that's why. Well, one way, I think we still not finalized yet, but this is a good way for us to figure out what could have, if there's something wrong with our model. So it's the histogram of detections, and on the x-axis is the confidence, y-axis is the number of detections. And when we want the peak to be as sharp as possible and as towards the right as possible. But over time, it starts flattening out, and then yeah, the peak starts moving towards the left. And that's where we get the trigger that, yeah, we need a new model run or new iteration. And this seems to work for us for now, but this is not the end of it. We, with this, we are able to get a more stable system, and yeah, we are good for now. But we do have further challenges that come up ahead. So we want to automate most of our MLOps pipeline. So what we do is we want to use foundation models like SAM or Dino to automatically annotate images that come in, and also have quality gates that make sure that the images that we don't support don't get to the model, and we are able to catch it before it comes out, and let the farmer know that there is a problem with the images, please clean the lens or something like that. The other one we want to explore is have more quantifiable performance metrics to enable automated alerts from Datadog or something else. And the final problem is the scariest one of them all, because model saturation is basically the inability of the model to learn more new things. So because it's a small model, there is a limit to which it can learn. So what we do is we could either go for a bigger model and sacrifice the speed, or we can sacrifice flexibility and have a model for each customer, which is hard. So overall, we are able to build a stable system that churns out quality models as it goes. But yeah, for now, we can say that we have successfully put YOLO on a tractor. So if you have any questions, please ask. Thank you.